Okay. Late start. There were some problems today, technical problems. I hope now everything is okay. Right? Okay. So we continue. How? But wait a minute. Yeah, here it is. Okay. So section 16.1. That is what I what I planned to start during last lecture, but time was almost over. So today, I'll call it continuous functions on an interval. In fact, here we'll talk about partly about compacts and partly about segment. So Theorem 1, if K R is a compact set and F is continuous on K, then F of K is a compact set. And I guess I should write what is this notation. That is the set y such that y equals to f of x with x in K. So the set of values of the function f. Proof. So suppose yn is a sequence of points from f of k. Then yk equals to f of xk, k from 1 up to infinity, and xk belong to the set capital K. Now, since the set K is compact, is a compact set, and xk, k from 1 to infinity, is a sequence of points of K. There exists a subsequence why I wrote K. I'm sorry. Let me change to N as it was before. N. There is a subsequence x and k, k from 1 to infinity now. That is when k should appear, such that it has a limit as k tends to infinity x and k, and this limit, which is denoted by x naught, belongs to the set K. That is just the definition of compactness. So it was okay. So once again, we start from an arbitrary sequence of points of f of k. What means point of f of k? It means the point is equal to the value of our function f at a point of the set capital K. So there exists a sequence of points of the set capital K. But capital K is compact, hence there exists a subsequence of this sequence x and k, which has a limit, and this limit is in K. That is just the definition of the set capital of the definition of compactness of the set K. So this is we deduced from compactness. Now f is continuous at x naught, since by the condition f is continuous at every point of K. And what is continuous? Heine definition. So by Heine definition of the limit of continuity, Heine definition of continuity, let's say, we deduce that the limit as k tends to infinity f of x and k equals to f of x naught. And at what it means? So limit as k tends to infinity f of y and k, because f of x and k, that is y and k, equals to f of x naught, which is definitely in f of k, since x naught is in K. So given arbitrary sequence of points from f of k, we can find a subsequence y and k such that it has a limit in f of k. And that is precisely the definition of compactness now for the set f of k. And that is done. So we have proved the compactness of the image of a compact set. corollary. Corollary. That is called Verstras theorem. For continuous functions on a segment. If f is continuous on AB, then f is bounded and f attains its maximum and minimum on AB. Proof. So what means bounded function? Bounded function means boundedness. The set of values, so the set of f of x where x belongs to AB is bounded. Is bounded. That is the definition of boundedness of a function, if the set of values of that function is bounded. But AB, interval AB, is a compact set. Since it is bounded and closed. Bounded and closed. And section 15.2, last section of former lecture. Hence, by Theorem 1, f of AB, just our set, f of x, x and AB, which is precisely f of the interval AB, is bounded. Is compact, so is compact. Hence, again by section 15.2, f of this interval is bounded and closed. So boundedness gives boundedness of the function f. And now what is about maximum and minimum? So f of the interval is bounded, hence there exists supremum f of x, xa in and b, and infimum, both are finite. And what we have to prove is, in fact, this supremum is precisely maximum. So the supremum is attained. There is a point in the segment AB such that f equals to its supremum at that point. If an interval is not the segment, it might be not true, right? Okay, I'll consider example a little bit later. So we have to prove that those values belong to the set of values. That is what we want to prove. That is what we want to prove. So the question is in this relation, that those numbers belong to the set of values. So consider M, which is supremum, let's say, right? So we consider just the supremum. For infimum, it's analogous. What means supremum? It means that for arbitrary epsilon greater than 0, there exists a point x in AB such that m minus epsilon less than f of x, of course less or equal than capital M. The point is that any number which is less than our supremum cannot be an upper bound. So now a consideration which was used many times. So we put epsilon equals to 1, 1/2, and so on, 1 over n, and so on, up to infinity, right? So every time we can find a point and we call it x1 here, x2 here, and so on, xn, and so on. So every time there exists a point in our segment AB, such that for the values we have the inequality. Which inequality? For epsilon equals to 1, m minus 1 less f of x1 less or equal capital M, m minus 1/2 less f of x2 less or equal capital M, and so on, m minus 1 over n less f of xn less or equal capital M, and so on. So we constructed a sequence of points xn in AB. AB no, I may do it shorter. Oops. Where is the eraser? Here, everything is here, okay. We'll proceed in a shorter way. So the sequence f of xn, what can we say about that sequence? Look, it satisfies those inequalities, and both the left hand side and right hand side tend to the same number, capital M. Hence, by two-policeman theorem, the limit of that sequence f of xn is equal to M. But the sequence lies in the set of values of our function, right? And this set is closed. Yeah, look, f of AB is compact, hence it is closed. Compact means bounded and closed. So from compactness follows this is closed. Closed. Closed means contains all its limit points, so all limits, and in particular the limit of that sequence. What is M? Hence, from closedness we can deduce that M belongs to this set of values. So M is a value of our function, and that is precisely what we wanted to prove. Okay, and maybe to illustrate why we spend the time, because, for example, consider f of x equals to x. That is definitely a continuous function everywhere, right? And we'll consider it on an interval 0, 1. So f is continuous here, right? But supremum for x in the interval f of x equals to 1, obviously, right? Because 1 is greater than every value, but every number which is smaller than 1 cannot be an upper bound for this set, right? So supremum is precisely 1, but it is not a value of function on that set. So the function does not attain its maximum on the interval 0, 1. But it's impossible for a segment. That is what Verstras' theorem says. Okay. Now, next property is called Theorem 2, intermediate value. Intermediate value theorem. If f is continuous on an interval let's say I will be denoted this interval I, and let's say f of x1 equals to c, f of x2 equals to d, where x1, x2 belongs to the interval I, then for any value let's say eta between C and D, there exists psi between x1 and x2 such that f of psi equals to eta. That is the intermediate value theorem. And if f is constant, then m isn't a limit point. Yes, good, very good question about. Yeah, I guess this question is very good for. Yeah, yeah. So, very good question. Yeah. So the question is, what happens if capital M is not a limit point? When it can be, when it can happen? Look, here we have limit of a sequence equals to M, right? So if infinitely many of those f of xn are different from M, right, then capital M is a limit point, and this consideration is true, right? When this is not true, if all those values except for finitely many are equal to M, but if those values are equal to M, then we don't need to prove anything, right? Because M is in this set. So we want to prove that supremum belongs to this set. And if values of f of xn equals to M, then M is in the set of values of the function f, right? We don't need to prove then anything. In particular, that is true when f is constant, right? So if f is constant, we don't need to prove anything, right? Supremum is definitely coincides with maximum and with minimum, so everything coincides. Yeah, but it's a good question indeed, right? Yeah, so this equality doesn't mean that M is a limit point. That's true. It is either M equals to those values or M is a limit point. That is better. Yeah, thanks for the question. Good. Okay. Yeah, now we have a intermediate value theorem, right? Proof. So let's suppose x1 less than x2. In fact, here it doesn't matter, we just choose an order. Then f is continuous on a segment x1, x2, which is in our interval I. So f is continuous on the interval I, and the segment x1, x2 is a part of that interval, hence f is continuous. Now, let us consider a particular case. Consider a particular case c less 0 less d and eta is 0. This is a very particular case, of course, right? Now, so it means we want to prove that there exists a point xi in the interval x1, x2 such that f of xi equals to 0. That is what we want to prove. Now proceed by dividing by half, by section. So let me draw the interval x1, x2, right? Divided by, denoted by I1, let's say, right? x1, x2. Divided by 2 equal parts. So here is the middle, x1 plus x2 over 2. Look at the value, f of x1 plus x2 over 2, right? There are three possible cases. Either it is positive or negative or 0. Let's proceed without break, right? Because we lose the time. So either positive or negative or 0, right? Look, f of x2 is d, right? So here the value is positive, here it is negative, right? So if it is 0, then we are done. We want to prove there exists a point somewhere where the function equals to 0, right? So if it is 0 here, then we are done. If it is positive, then for the left half, what we have? It is negative at one end and positive at other end of this half of interval. If it is negative here, then we can consider another half. So precisely one half has the same property as I1. Namely, okay, let's say here it's positive, then we have, that is I2 now, right? So denote by I2 a half of I1 such that the product of values of f at the ends of I2 is negative. So different signs, opposite signs, is equivalent to say that product is negative, right? And we can continue, right? Repeat it. So divide by half. Again, look at the value at the middle. If it is 0, then we stop, we are done. Or we continue. So if we will not stop, so the process will continue up to infinity, then it means that we construct a sequence of nested intervals. I1 contains I2 and so on, right? And if we'll denote, okay, let's say x1, x2, right? So I k is interval x1k, x2k, right? That is ik. So the limit as k tends to infinity of the difference x2k minus x1k is 0, because every time we divide by 2, so x2k minus x1k is equal to x2 minus x1 over 2 to the power k minus 1. So every time we divide by 2. For k equals to 1, it's precisely x2 minus x1. The limit is 0. So that is a sequence of nested intervals. By the counter nested interval principle, so nested intervals principle says there exists an intersection of those intervals is not empty. The intersection is not empty. So, and in fact it consists just of one point, so xi belongs to this intersection. Now look, xi belongs to the intersection. It means for arbitrary k natural, x1k less or equal xi less or equal x2k. Xi belongs to the interval ik. That is what is written here. Now, look at the construction. You see that difference between x2k and xi, which is non-negative, is less or equal than x2k minus x1k. So tend to 0, left and right hand sides, right? Hence, this tends to 0 as well. So you see, x2k tends to xi, x1k tends to xi also, right? So limit as k tends to infinity, x1k equals to xi, and that is also equal to the limit of x2k. But by the construction, f of x1k was always negative, and f of x2k was always positive. Hence, their limits are non-positive and non-negative correspondingly, because when we take a limit in inequality, we cannot preserve strict inequality, but the sign of non-strict inequality is preserved. So we obtain that limit as k tends to infinity, f of x1k, which is by continuity is f of xi, is non-positive, and analogously limit as k tends to infinity, f of x2k, which is again by continuity f of xi, is non-negative. And those two inequalities give us precisely what we want, f of xi equals to 0, right? And of course, other case for C and D, I mean, C is positive, D is negative, is considered absolutely analogously, right? Now, for the general case, what we should to do, for the general case, I mean, if eta is not a 0, and C and D are arbitrary, what we can do, So, general case, consider let's say g of x equals to f of x minus eta. This is also continuous on the interval I. Now, g of x1 is f of x1 minus eta. G of x2 is f of x2 minus eta. And we know that eta is between C and D, that is C minus eta, D minus eta. So it means that their product is negative. G of x1 times g of x2 is negative, because signs are opposite. So the values of the function g are opposite at x1 and x2, and we can refer to the case which was proved. So there exists psi, between x1 and x2 such that g of psi equals to 0. And now go back to the function f. We obtain that this is precisely f of psi equals to eta, what we wanted to prove. And that's all. That's the end of the proof. So let me have a look at problems. Okay, example. There is an example. Okay, I'll erase it. Example 1. Prove that the equation e power x equals to minus x has at least one real solution. So what we have to consider? Look, here we can take as interval just the whole real line. That is also an interval, infinite interval, right? So now look at the function f of x equals to e to the power x plus x. That is a continuous function, although at the moment we don't know it. I'm sorry for that example, because we didn't construct yet that function. We know what is e, but we don't know what means e to the power x yet. Okay, somehow I'll refer to the future. We'll do it in the future. So, but at elementary school, you're not elementary, secondary school, right? I don't care about which part of school where you considered powers. So somehow you understand what is power. Of course, we have to prove that this function is continuous. That is another question. We'll do it later, in fact. So, bad example, very bad example. Sorry, I wrote it. And now, look. So, suppose that we proved somehow that this function e to the power x is continuous. We'll do it later. And then look at, let's say, f of 0. F of 0 is e to the power 0 plus 0, so it's 1. Positive. And f of minus 1, e to the power minus 1, that is 1 over e minus 1. E is greater than 2, so that is negative. Hence, there is, according to the first part of the proof, there is psi. In fact, even we know it is in the interval minus 1, 0, such that f of psi equals to 0. And that is precisely e to the power psi equals to minus xi. So that is how intermediate value theorem works. Of course, we cannot solve this equation, in fact, explicitly. It's impossible. No way to write down an explicit solution. Numerically, of course, you can. Okay, that is about continuous functions on an interval. Yeah. And now, next section. Okay. So section 16.2. 16.2. Continuity of the inverse function. So I'll start with general definition. Okay. If a function f from x to y has the following property. First, for every y in y, there exists x and x such that f of x equals to y. So y is precisely the set of values. And secondly, if f of x1 equals to y, f of x2 equals to y, x1, x2 are in x and y is in y, then x1 equals to x2, then there exists then the function f minus 1 from y to x, which has the property f minus 1 of f of x equals to x for all x and x, and f of f minus y of y equals to y for every y in y is called an inverse function for f. Of course, there is a proposition. The inverse function exists. Of course, for under conditions 1, 2. We have to remember about those conditions, of course, right? Okay, so proof. So look, 1 and 2 guarantee that for arbitrary y in capital Y, there exists unique. I didn't use yet this symbol. There exists and unique. There exists unique x in x such that f of x equals to y. Why? Because there exists according to the first, and it is a unique y, because if there are two such x's, then they are equal, so there exists only one. And we'll denote x by definition as f minus 1 of y. And that's all, in fact, right? So we define x like that, and then f of f minus 1 is precisely y, and conversely, f minus 1 of f of x is x. That's all. Okay, now main theorem. Theorem 1. If f is strictly increasing, decreasing, and continuous, on an interval I, then it has an inverse function f minus 1, which is continuous and strictly increasing or decreasing on the interval f of I. So we consider a function which is strictly increasing or decreasing and continues on an interval, and we want to prove that it has an inverse function. So proof. First of all, let's check that all conditions of our definition are satisfied, right? So we take x equals to I and y equals to f of I. So first condition is satisfied automatically by the definition of capital Y, right? Because y is precisely the set of values, right? Something new? No. Okay. So, first condition is satisfied. And for the second condition, look, we know, for example, if f is increasing, x1 less than x2, then f of x1 less than f of x2, right? So if x1 and x2 are different, then the values are different as well. So it means that once we have same values for two values of x1 and x2, then definitely x1 equals to x2. So both conditions are satisfied. Hence, there exists, by proposition, there exists f minus 1, which is from f of I to I. So the inverse function exists. Now, what is about strictly increasing or decreasing? Look, if we have, let's say, y1 less y2, y1, y2 belongs to f of I, right? Then y1, y2 belongs to f of I means there exists x1 and x2 in I such that y1 is f of x1, y2 is f of x2, right? Now, suppose x1 greater than x2, and in fact it means that x1 is f minus 1 of y1, x2 is f minus 1 of y2, inverse functions. Suppose x1 is greater or equal than x2, right? Then, by increasing, so if f is increasing, then f of x1 is greater or equal than f of x2. And that is y1, that is y2. And that is a contradiction. So it means the supposition x1 less or equal x2 is not satisfied. So x1 is less than x2. And it means f minus 1 of y1 less than f minus 1 of y2. So we took arbitrary y1 less than y2, and it implies f minus 1 of y1 less than f minus 1 of y2. So indeed, inverse function is strictly increasing if f is strictly increasing. Now, what's about continuity? And what's about that f of I is an interval? So, in fact, I considered here f is increasing, so let's continue. So we suppose f is increasing. Still suppose f is increasing. Right? I want to prove that in fact f of I is an interval with ends infimum f of x, x in I, and supremum. I don't claim that those infimum and supremum are finite. Need not, right? Because, for example, f of x equals to 1 over x on interval from 0 to infinity, right? It's strictly decreasing, but supremum is plus infinity. So, need not be. And how to prove that it is an interval? So, by contradiction. And what is a contradiction? Suppose there exists y in an interval, in the interval from infimum to supremum, such that for all x and I, f of x not equals to y. So y is not a point in f of I. So, y is a point of an interval between supremum and infimum, right? So, y is less than supremum, hence there exists, okay, x2 in I will start with x2 to have x1 less than x2, such that y is not an upper bound for the set of values of f of x. So y is strictly less than supremum, hence y is not an upper bound. Hence there exists a point such that y is less than f of x2. That is from the property of supremum. Analogously, since infimum is less than y, hence there exists x1 in I such that f of x1 less than y. So now, by the intermediate value theorem, if x1, x2 are 2 points of our interval and function f is continuous on our interval, hence y is between f of x1 and f of x2, hence there exists xi between x1 and x2, and in fact for increasing function we can be sure that x1 is less than x2, such that f of xi is precisely equal to y. And that is a contradiction, right? So it means that indeed the set f of I is an interval. We don't care about ends of that interval yet, doesn't matter. But okay. So yeah. Now we have proved that the inverse function exists. It is strictly increasing or decreasing on the interval. So the only thing remains is to prove that it is continuous. I have 5 minutes. What to do with 5 minutes? Yeah, maybe I'll continue the proof next time. It's not good. First time when maybe I'll change the title of the section then, right? That is the existence of the inverse function. So the theorem says about continuity, but I didn't touch the continuity yet, although I used continuity, right? To prove that it is an interval, I have to use continuity. But nevertheless, for a while, the proposition was about the existence, and here we have proved up to now the existence. And also, okay, maybe I'll continue the proof next time, but for a while it's sufficient time to write down a remark. The supposition of continuity is not necessary to prove the existence of the inverse function on f of I and its strict monotonicity. So look at the part which is written here. In fact, nowhere I used continuity on that blackboard, right? Just increasing for the existence, or decreasing, of course, analogously. For increasing, nowhere I used the continuity. Of course, here, look, I didn't write the interval. Need not to be an interval, right? If a function is strictly increasing on an interval, the set of values need not to be an interval, right? That is obviously, let me write an example which shows that indeed you need not to write. So let's say interval AB, and the function is like that, right? Somewhere here, yeah. So you see the set of values has a gap. So the set of values is not an interval, right? But so you see that if you forget about continuity, then definitely you cannot assert continuity, right? And also you should omit the interval. But everything else is valid. So if function is strictly increasing on an interval, then it has an inverse function, which is also strictly increasing on the set of values. That's all for today, and we'll continue next time. Okay, thank you for your attention.